Okay, so contact stress. Contact stresses causes erosion, wear of the surface of the geared tooth. Um, I'm not going to derive how they went into this calculation because it is a giant pain in the ass, and a function of various things. So we got the Young's modulus for the materials. We've got the Poisson's ratio for the two materials. Uh, we've got the diameter, got the pressure angles, so on and so forth. So essentially, you press two surfaces against one another. How flexible those things are, kind of how much they move relative to one another. Uh, Obviously, what sort of force is applied, all comes into play. So, what sort of contact stress occurs is based upon all those factors. But what they do here is they kind of took a whole bunch of those terms. So all these terms right here, those are all functions of the material properties of the, um, they're functions of the material properties of the gear and the pinion. So essentially, what they did is, well, we got tables for that. So if we are looking for the CP of a gear combination where we've got steel on steel, then we're looking at 2,300, and the units there are let's see, they're they're the square root of pounds divided by an inch, or psi to the 0.5, taking a square root of our psi there. So we got steel on steel, we got steel on cast iron, we got steel on aluminum bronze, got steel on tin bronze. Obviously, you got tin bronze on tin bronze, so on and so forth. So this is for the pinion, this is for the gear. And if we're looking for metric, again, units are going to be in pressure to the power of 0.5. So MPa to square root of MPa. But steel on steel, tin bronze on tin bronze, aluminum bronze on aluminum bronze, so on and so forth. So, based upon that, this formula here gets a bit simpler. So we got our CP times the tangential force, and then these two functions of the angle and the diameters of the pinion and the gear. And then we've got the the width of the gear, and then again cosine of the pressure angle. So essentially that can all be kind of reduced down if we plug in this I. So if we plug in this I here, sine of the pressure angle, cos of the pressure angle divided by 2 times the gear ratio divided by the gear ratio plus 1. Plug that in, and this reduces down to, well, it reduces down to this part here. And then there's a few correction factors that they threw on as well. So a relatively complicated formula got a bit less complicated by making a few intermediate calculations. So again, so we got our CP, which is a function of the materials. We got our I here, which is a function of the pressure angle and the gear ratio. We have our width of the gear, got the diameter of the pinion, we've got the tangential force, and then we've got these three correction factors here: kV, KO, KM. Guess what? We saw those already. We saw those when we were talking the fatigue failure. Those occur here too. So we're going to use, those are the same ones. Same calculation, same values used. So yeah, just scroll back up in the slides to go find those, or flip a bit back further in your textbook to find what those are. So again, we've got some sort of stress level here, and we need to compare that to some sort of strength in order to figure out what our safety factor is. So the strength value here we're going to be using denoted SFE. So that SFE, again, this is kind of like in test conditions. That's a material property, so you can look it up for the various materials we're talking about. In general, for most stuff that you're going to be working with, you might be using this empirical formula here to calculate it based upon your Brunel's hardness number. So for steels, nodular iron, for some cast, if you're using a particular grade of cast iron, and so on and so forth. If you have used a steel that has been hardened, case hardened, then you use the Brunel's hardness number at the surface of that material. So if you do case hardening, it's basically you already took 333. I'm sure Duke's talked about that, so I don't need to go into it too much. But you got localized hardness at the surface that doesn't make its way into the core of the gear, but it's harder on the surface, so it's going to resist its surface. It's going to have a higher surface fatigue strength. So that having said, we don't use just that. Obviously, we've got other factors that we throw in there too. Not quite as many as the other ones. So what we actually use here is the SH here. Compare the SH to the sigma H. So got this material property. We also adjust it based upon the how many cycles we're designing for. So if that's our Li, and then we also adjust it for the reliability. So the fatigue life correction factor, that one is the CLI. That is based upon, basically, if we're designing for 10 to the 7 cycles, then that's going to be 1. If we're trying to design for more, then our CL drops, so basically our apparent strength drops. If we don't need it to last as long, then it goes up. And if you're wondering what happens beyond this chart, it's basically a flat line for anything less than 10,000 cycles. So we got that. Again, this is for this is a general shape. You may have better data for the particular type of steel you're working for. So if you do have it available, then use that. If not, use this. And then we got our reliability factor. I use CR instead of KR in this one. Again, not sure why the switch. It uses a different CR than the one that was originally used, than the one that was used last time, than the one that was used for the fatigue strength of the gear teeth, and for the previous, like the the CR that we'd seen previously for shafts or welds or what have you. So I don't know why they didn't keep the CR on the bending strength calculation and use KR here, but whatever. That's I didn't write the textbook. So anyways, if we're aiming for 99% reliability, we use a CR of 1. If we're only going for 50% reliability, CR of 1.25. If we're going for 99.9, 80. 80%. So we got those, again, mean strength, O, B, calculated based upon what we saw previously. Got our I, that's just a function of the geometry. Got our CP, that is a function of the materials used. Our SFE is a function of the materials used and typically calculated based upon our Brinell's hardness number. CLI, for LI for life, that's based upon how long we expect this thing to last. If we're at 10 to the 7, it's 1. And then our CR is based upon what sort of reliability we need. If 99% of our gears need to last that long, then we're going for 1. And then from there, we can calculate, if we have a mandated safety factor, then we can say, all right, our stress level is lower than our strength level divided by our safety factor, so we're good. Or if we're trying to figure out what our safety factor is, then obviously we'd rejig that calculation. But typically speaking, 1.1 to 1.5 is usually sufficient to guarantee fairly high reliability. And one thing to keep in mind for the erosion here, like it's a less catastrophic failure than you would see with your bending failures, your bending fatigue. The tooth doesn't break off; it just slowly wears away. So you can see some very worn gears that are still working well in operations. Generally speaking, usually gears are more prone to failure via surface fatigue than they are to the bending, the bending crack growth, which is why you do tend to get case hardening, because case hardening allows you to essentially apply heat treatment that targets the weak spot. It targets our surface fatigue. It increases the hardness of the surface, while not really touching the the strength in the core, where we base our calculations for the whatchamacallit. What am I trying to say here? For the bending fatigue on. So we don't have to, we don't have to use a stronger material throughout the entire thing, which would of course ramp up costs. We can just selectively pick, all right, selectively do something that effectively increases the strength, the overall strength of the gear by hitting the weak points.